To support the volume of data moving through cloud-native applications and 5G telecommunications networks, modern infrastructure must handle hyperscale throughput. Historically, the intelligence driving this data was trapped inside the hardware. In a traditional network architecture, every individual router and switch houses both a control plane and a data plane. Each device independently executes complex routing protocols, like OSPF and BGP, to calculate paths and forward packets. This distributed model requires engineers to manually configure each device through vendor-specific command line interfaces. Implementing a network-wide policy change means logging into dozens or hundreds of separate boxes. As enterprise architectures embraced large-scale virtualization, this manual per-device configuration model became inadequate. Updating isolated hardware one by one is too slow for dynamic environments and increases the likelihood of human error. Software-defined networking resolves this bottleneck through a formal structural split. It decouples the network's decision-making intelligence from the physical hardware, allowing the system to be managed and automated programmatically. Operational efficiency at a modern scale cannot be achieved by managing fragmented hardware boxes. It requires a centralized software architecture that orchestrates the infrastructure as a unified whole. Building an SDN architecture begins by separating routing logic from the actual transmission of data. This is the three-plane model. At the bottom is the data plane, where hardware devices become simplified forwarding elements. That extracted intelligence moves upward into the control plane. A single software application, the SDN Controller, now assumes responsibility for global topology mapping and path calculation. This separation allows layer optimization. The data plane focuses exclusively on processing packets with minimum latency, while the control plane dedicates its computing power to sophisticated business logic and security policies. Because the intelligence is centralized, administrators gain a real-time global view of the entire network topology. They no longer rely on the fragmented, localized routing tables of individual devices. Abstracting the network's brain from its muscle allows engineers to govern the entire infrastructure using holistic software policies, escaping the physical limitations of single nodes. Centralizing intelligence is only effective if the controller can communicate with the rest of the stack. The controller connects through directional APIs. Southbound APIs reach down to the hardware, pulling telemetry up and pushing Yang-modeled flow rules down. Northbound APIs reach up, allowing high-level applications to push abstract business intent down to the controller using standard HTTP methods. Applications requiring higher quality of service for critical video sessions send requests through Northbound APIs. The SDN controller receives the request and automatically implements the necessary traffic shaping rules across the infrastructure. These APIs translate high-level business strategies into physical network actions across multi-vendor hardware. Historically, administrators monitored network status using SNMP, a protocol that pulled devices for updates but struggled to execute complex configurations reliably. The industry has replaced this with model-driven programmability, utilizing the structured, predictable Yang data modeling language. Modern southbound communication uses two protocols. Netconf provides transactional operations. If a multi-step configuration fails midway, it rolls back the entire operation. Conversely, gNMI uses streaming telemetry. Instead of constant polling, switches proactively push binary data to the controller only when thresholds are met.
Streaming telemetry eliminates continuous polling, reducing network overhead and minimizing CPU load on individual devices. Relying on these structured, model-driven protocols ensures that configurations are predictable. Without this transactional safety and precise telemetry, automated scripts could rapidly deploy configuration errors across an entire enterprise. Scaling automation introduces data management challenges. If input data is inaccurate, the network will be configured incorrectly. To solve this, organizations deploy a network source of truth. This is a centralized database serving as the absolute definitive reference for exactly how the network should be configured. Platforms approach this data differently. Netbox focuses on static documentation. Nautobot acts as an active engine, integrating deeply with GitOps workflows. The source of truth feeds configuration tools. Ansible is stateless, pushing playbooks across multi-vendor switches without retaining prior state. Terraform is stateful, comparing desired code against its local state file to automatically modify or destroy virtual resources to match the target. In a mature automation pipeline, engineers do not configure physical devices directly. They update the code in the source of truth, and automation tools propagate that desired state down to the hardware. The ultimate objective of this architecture is intent-based networking. In this environment, operators stop specifying step-by-step technical configurations and instead define high-level business objectives, the intent. The platform achieves objectives through a closed-loop cycle of visibility, insight, and action. First, a switch streams a latency anomaly. An AI evaluates this insight, then immediately instructs the controller to push a new flow rule, rerouting traffic, successfully completing the self-healing loop. Centralizing the intelligence that powers this closed loop introduces a structural vulnerability. The controller becomes a massive single point of failure. Attackers frequently target the memory limitations of physical switches through flow table exhaustion. Flooding a switch with forged traffic forces the controller to install overwhelming fake rules, dropping legitimate packets. Protecting the controller requires rigorous hardening. Engineers implement mutual transport layer security to encrypt the control channel, ensuring only authorized devices communicate. They also rate limit messages sent upward, preventing denial of service attacks. True autonomy demands that a network heal from physical failures while simultaneously applying mathematical distrust to every internal command it generates. The most significant barrier to deploying these autonomous systems is no longer technological capability. It is a severe human skills deficit. Managing programmable infrastructure requires a new discipline known as net DevOps. Organizations need engineers who possess a combination of traditional routing protocol expertise, advanced software development skills, and AI literacy. This rapid transition carries operational risk. If junior engineers rely entirely on automated platforms to manage the network, they lose the hands-on troubleshooting experience and critical thinking skills necessary to diagnose complex, low-level protocol failures. To build this expertise safely, engineering teams begin by writing simple Python scripts for tasks like configuration backups, paired with investments in infrastructure as code training. Managing massive data throughput requires shifting from manual CLI inputs to programmable, intent-based software. This shift replaces static hardware management with dynamic, software-driven oversight, requiring engineers to master both routing protocols and the code that automates them.